Okay, so let's look at this example. So this is a true or false question. Does a power series have to converge uniformly to a continuous function on its domain? That's the question. And the motivation for this is we're comparing it to the theorem that we proved here that said that a power series converges uniformly to a continuous function on any compact subset of its domain. So we know that on a compact subset of the domain, our power series will converge uniformly. The question is, what about on just the whole domain? And the answer, of course, is going to be false. So let's go through an example which shows that a power series can fail to converge uniformly on its domain. And you can probably guess which power series we're going to use. We're going to use the geometric power series. So let's consider, let's just say f of x equal to, we're doing x to the n, 0 to infinity. So we know that our series, so for each n, fn of x is going to be x to the n, and the series fn converges to 1 over 1 minus f on compact subsets of the domain. However, our series does not converge uniformly on our domain. Okay, now let's try to prove this. In order to prove it, we need to look at the negation of a series converging uniformly to a function on a set. So let's see here. So recall our series Fn converges uniformly to f on S if and only if for each epsilon greater than 0, there exists an index n such that n bigger than n implies for all points in S, the distance between your nth partial sum and your limit function is less than epsilon. So if we take this definition, this epsilon n definition, and we negate it, what will we get? So let's see here. So now we want to say this does not converge uniformly in S if and only if it is not the case that this happens, which is if and only if. Now the negation of for each epsilon there exists an n such that all of this happens is there exists an epsilon such that for each n this doesn't happen. Okay, so there exists epsilon greater than 0 such that for every n, now what is the negation of this? Well, this is saying if n is bigger than n, then this happens. So the negation of that would be there's an n bigger than n, and this doesn't happen. So there's an x in S, sorry, this distance is going to be bigger than or equal to epsilon. Okay, so we want to show there exists an epsilon where regardless of how large n is, we can always find an index after it where there's a point in our set where this distance is bigger than or equal to epsilon. So for us, let's go back in and fill in that S is going to be the interval -1 to 1. Our f of x is going to be 1 over 1 minus x. Remember, f of x is, it'll be the pointwise limit, right? And if you're trying to prove that your series converges pointwise but not uniform, then that the convergence is not uniform, use that pointwise limit for f. And now the fk's are just x to the k. So this top right here is just going to be, and this actually, we should be starting at 0. Sometimes your series starts at 0, sometimes it starts at 1. Here, this will be 1 plus x squared plus dot, 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 all the way up to x to the n. So if I'm looking at the distance, this is going to be 1 plus x squared plus dot, 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 plus x to the n minus 1 over 1 minus x. And I can simplify that. Cross multiply, get a common denominator. And when I multiply this by this, what do I get? I'll get 1 minus x to the n plus 1. And then I'll have minus 1 also in my numerator. So this is actually going to be equal to negative x to the, I can just write x to the negative x to the n plus 1 divided by 1 minus x. Okay? So I'm looking at showing that there exists epsilon greater than 0, such that for every n, there exists a little n bigger than n, and there exists an x in -1 and 1, such that negative x to the n plus 1 over 1 minus x is bigger than or equal to epsilon. Now it turns out that this will be true for any epsilon greater than 0. In terms of easy computation, I'm just going to try to prove this for epsilon equals 1. So let's try to prove this for epsilon equals 1. There's nothing special about choosing epsilon equals 1. We could also try it for epsilon equals 100 or epsilon equals, 0.1, right? I'm just using 1 because it's easy to, it's easy for my computations. So I want to prove that for every n, there's an index after it and a point in my domain where this is bigger than or equal to 1. I really don't need that negative, right? So I can rewrite this as, I'm just going to cross multiply. I can rewrite it as the absolute value of x to the n plus 1 bigger than or equal to absolute value of 1 minus x. Okay. So think back to the behavior of x to the n on even 0, 1, right? Now remember, I just need to show there's an x in this domain here. So if I look just at the behavior of x to the n on 0 to 1, that works because that'll be a subset of the whole domain, right? So let's just try to draw. Now, y equals x is just going to be a straight line. And then y equals x squared is like a parabola, right? And then the cubic function is flatter, but it still has to end up at 1, right? And so the x to the n, it starts off smaller, but then once it hits 1, it is steeper, right? The lines cross. So this is x squared, x cubed, x to the fourth, and so forth and so on. This point here is 1. This point here is 1. Now, contrast that to 1 minus x. What does 1 minus x look like? 1 minus x, of course, is going to be a line with a negative slope. And it's going to be a line that goes through this point here. And it's going to hit here at 1 comma 0. So let me maybe use a different color. So this is my 1 minus x. Yeah. So the question that I'm asking is, for any value of n, can I find an index after it and a point where the line, right, so say if here's x to the n is bigger than 1 minus x, or x to the n plus 1, right? So like if x is back here, then x to the n plus 1 is going to be really small, and 1 minus x is going to be really big. So we're going to be looking for values of x that are getting closer and closer to 1. Because the closer x is to 1, that's when this starts to be closer to 1, and that starts to be closer to 0, right? So for each n, the bigger this n gets, the closer to 1 I'll need to choose a value where x to the n plus 1 is going to be bigger than the value of 1 minus x. So I can even see here that I can let n equal, right there exists n, just let n be big N plus 1. So what I'm thinking is, we'll try for each n, let little n equal n plus 1. And x, now I don't know, let's see here, I don't know, I'm trying to think of a way to come up with a formula for x to ensure that this is going to be bigger than 1 minus x. And I think what'll work is if I have x bigger than 1/2, right? Now that will be less than 1/2. So follow me here. If x is bigger than 1/2, 1 minus x is going to be less than or equal to 1/2. So now I just have to guarantee that my x to the n is bigger than 1/2, and x to the n plus 1 is bigger than 1/2. Right? So this is how we reason through this. So I need x to be bigger than 1/2. I need x to be less than 1. And I need x to the n plus 1 to be bigger than 1/2. Okay? To guarantee that x to the n plus 1 is bigger than 1/2, what if we just take natural log of both sides? Right? So, natural log, n plus 1 times the natural log of x needs to be bigger than the natural log of 1/2. Okay, so natural log of x needs to be bigger than the natural log of 1/2 over n plus 1. So x needs to be bigger than e to the natural log of 1/2 to the, oh, I could have just taken the n plus first root, sorry, to the 1 right over 1, n plus 1, i.e. x is bigger than the n plus first root of 1/2. Okay. So I'm going back to my goal. This is my goal. This is what I'm trying to show. Right, my goal. Let's try to prove this for epsilon equals 1. So for each n, there exists a big N. I'm going to let n equal n plus 1. Little n is going to be big N plus 1. Then that is a number that's bigger than n. And now what am I going to let x equal? Okay, if my little n is going to be big N plus 1, that means really I need absolute value of x to the big N plus 2 to be bigger than or equal to 1/2. Okay, now that means I need x to be bigger than the n plus second root of 1/2. Okay, so what is my x? My x is going to be 1/2, 0.5 to the 1 over n plus 2. Then that will be less than or equal to that. So let's go ahead and write it all out. Okay. So we're putting everything together. This is false. And we're saying consider x to the n equals 0 to infinity on negative 1, 1. For epsilon equals 1, for each n in n, let little n equal n plus 1 and choose x equal to 1/2 to the 1 over n plus 2. Then the distance between 1 and x is going to be less than or equal to 1/2, and that is going to be less than or equal to x to the n plus 1, right, which is the same thing as absolute value of x to the n plus 1. So this is less than or equal to this. So 1 is less than or equal to 1 minus x. That should be a 2. 2 plus 1 plus 1. All right? But remember, that was the distance between x to the k and 1 over 1 minus x. So our series does not go uniformly to 1 over 1 minus x on S. So we would put in here, we need to put in here note x belongs to S and n is bigger than n, right? Now, in the remaining few minutes, what I want to do is go to Desmos and show you what these functions look like. Not my little crazy sketch, but, excuse me, let's look and see what it looks like. Okay, so this is just going to be x. This is going to be x squared, x cubed, x to the fourth. Let's do x to the 10th, x to the 100th, right? And then the next one we need is 1 minus x, okay? Now, I only care about the domain from -1 to 1. And you can see here that due to the symmetry, really I just need to focus on 0 to 1 because I'm looking at the absolute value, right? So let me adjust and have this go just from 0 to 1. And let me have my y-axis go from maybe minus 0.5 to, 1.5. Okay. Okay. So you can see what's happening here. If you look at x, that's the orange, and then x squared is in blue, x cubed is in green, x to the fourth is in purple, x to the 10th is in black, x to the 100th is in red again, right? So remember I was saying that the higher your power of your monomial, the flatter it becomes, right? It's hugging close to the x-axis, and then at the last minute it kind of has to shoot up to get to 1 because all of these monomials have to hit the point 1 comma 1, right? So when we're asking, if we look back at our paper here, we're asking for every n, or for the zeros, this, and epsilon, such that for each n, we can find an index after which this is bigger than or equal to epsilon, right? The absolute value of this. That means we needed that bigger than or equal to that. And looking back on our graph, yes, for any index n, if we pick a monomial big enough, right, x to the, 898 or something, right, 888, that's going to be green. Look, you see it almost looks like a square. If we go far enough out, the higher n is, the further out we're going to have to go. I want to zoom in just so we can see, because you might be thinking that x to the 888 actually went to 1. It doesn't go to 1. Let's do point. Let's do point 9. I'm going to do point 9. See? 0.99 or 0.95. Can you see now how even for x to the 888, say our big N is 888. For x to the 888, remember 1 minus x is in blue, right? So we would have to go out to like 0.995. That's when x to the n plus 1 is going to overtake 1 minus x, right? So because our domain is an open set, we can't guarantee that we'll always be able to have the distance between our partial sums and that limit function within epsilon. If we had a compact subset, then we'd have a cutoff. And once you have a cutoff, you no longer have those functions racing up to the point 1 comma 1. So you have more control over their growth. And you can say, oh, okay, well, after this point, everyone is going to be close to 1 over 1 minus x, right? But as it stands, if our domain is allowed to go all the way up to 1, then the higher we get in our partial sum, the functions are going to stay close, but then they're going to leave, right? They're going to leave that epsilon tube. Okay, so I hope this has been, I wanted to go through this with care, this example with care to make sure you understand it. It's one of those crucial examples that really highlights the concepts of series converging. It highlights the concept also of uniform versus pointwise convergence. Okay, so a question on an exam would be, could ask you to come up with a specific value of little n, and I give you a value of big N. For big N equals 100, what little n and what x would show us that the series doesn't converge uniformly, right? And that'll let me know if you really, really, really understand the mechanics of the proof. As usual, let me know if you have any questions.